Hello students, in this video we'll solve the Dirichlet problem for the heat equation on a finite interval. Let's suppose we wish to solve the following boundary value problem. Our boundary value problem is partial u partial t is uxx. I would like to have u of x 0 being equal to some given density function f of x. In other words, I know the temperature at time 0 along the x-axis. This is going to be valid for x between 0 and pi and t greater than or equal to 0. That's the domain of our boundary value problem. And I would like that u of 0 in t to be equal to u of pi in t to be equal to 0. So physically, what does this represent? So physically, we have the following situation. So I have a wire of length pi. So here's 0 up to pi. Here's the t-axis over here. That's the time axis. And I give you some initial temperature distribution. So there's a temperature distribution over here on this wire, right? And then at a later time t over here, so this of course is just the heat, this is just the heat equation. It follows from Fourier's law of conduction. And what will happen is as this function u of xt is going to give the temperature, so u of xt is just the temperature at the point x along the wire at time t, right? That's the temperature of that location over here. So in other words, at time 1, for example, you have the same wire, right? And now, of course, the heat is flowing in a different way, right? So based on Fourier's law of conduction, so that will tell us how the heat is changing along that wire over here. So in other words, I'd like to find solutions of this equation given an initial distribution of temperature, okay? Excellent, so let's do this. So our approach is going to use separation of variables as a classic technique, right? So I'm going to suppose that u of xt is a function a of x times the function b of t. I'm going to look for product solutions of this. That's the method of separation of variables, right? If I plug this into the equation, what does the right-hand side turn into? It turns into b prime of t, a of x, and then the right-hand side turns into what? It turns into a double prime of x, b of t, right? And so therefore, this tells me what? This tells me that b prime of t over b of t is equal to a double prime of x over a of x, right? Just by dividing by b and a, right? And now I have a function of t. This only has t's in it. It's a t function. And this over here is an x function. So the only way an x function can be equal to a t function, if I did the partial with respect to t, that'd be t's over here and be nothing over here. Then the partial with respect to x over here, I'd have nothing over here and something over here. The only way that can be the case is that these things are constant, right? They have to be constant lambda. And that lambda is called the separation constant. So this is like a separation constant. Okay, so the separation constant can be one of three things. It can be positive, it can be negative, or it can be 0, right? So let's rule out some of those cases, right? The first case we're going to rule out is the case when we have a lambda equals 0. So this is case 1. Case 1, lambda is equal to 0, right? Well, if lambda is equal to 0, that says that b prime is equal to 0 and a double prime is equal to 0. So I'm going to focus on the a. That tells me that a double prime of x is equal to 0. That tells me that a is a linear function, right? So a is going to be a constant c1 plus c2x, and therefore our solution, u of xt, will be that function b of t, whatever it happens to be, according to this equation over here, times what? Times c1 plus c2x, right? But I know that if I plug in 0, I need to get 0. So I know that u of 0t for any t is going to be equal to 0. So this implies that 0, which is u of 0t, is going to be equal, it's going to be a b of t times what? Times when I plug in 0 for x over, I get a c1. Since, of course, b in some sense, well, if b prime is equal to 0, that says that b is a constant, so that's going to force c1 to be equal to 0. So c1 is equal to 0. And if I plug in pi to this over here, I get that 0 is equal to u of pi t for any value of t, right? So that's going to be, of course, b of t times what's left over. So c1 was equal to 0 over here when we plugged in 0. And now I get that this, if I plug in pi, I'm going to get a pi times c2, right? And pi times c2 is going to be forced to be equal to 0, so that's going to force c2 to be equal to 0, okay? So the only solutions here, that forces a of x to be equal to 0, and that's not very interesting for us because I know that 0 is a solution to this, right? It's not going to help me solve the boundary condition, but I know that 0 is a solution. No big deal. So case 1 doesn't give me any information, right? The second case to consider is the situation when lambda is going to be positive. So if lambda is positive, so let's do that next case, case 2. lambda greater than 0. If lambda is greater than 0, I can write it as m squared for some positive value of m, right? It's a positive number, so I can square it. And then what's the A equation going to give us? The A equation, A double prime of x, is going to be equal to m squared times a, so that's minus m squared a of x is equal to 0. And I know how to solve this equation over here. This equation has solutions. This is just d squared minus m squared is equal to 0. So this is going to be that something that a of x is going to be c1 cosh of mx plus c2 sinh of mx. Okay? Now by the same reasoning over here, I need that a of 0. I need that a of 0 and a of pi have to be 0. So a of 0 is 0, so 0 is equal to a of 0. Well, that's going to force what? Well, I plug in 0, this I'm just going to get the sinh is going to go away. I'm just going to get cosh, so that's going to be a c1. That's going to force c1 to be equal to 0. So c1 is actually equal to 0. That's gone. And likewise, 0 is equal to a of pi, but that's going to be c2 sinh of m pi, and the sinh of m pi, if m is greater than 0, is not equal to 0. That's going to force c2 to be 0. c2 is equal to 0. There's no sinh there. So this, when lambda is positive, there are no solutions to this boundary value problem either, which leaves us with the last case, the most important case. Hopefully this will give us something interesting. The last case, of course, is case 3. So case 3. And what's case 3 going to be? Case 3 is when lambda is less than 0, lambda less than 0. And that says we're going to let lambda be negative m squared. And then our a prime equation becomes this. It becomes a double prime of x plus m squared a of x is equal to 0. I know that. That's going to be a of x is c1 cosine of mx plus c2 sine of mx. Okay? Now let's just think through what happens over here. When I plug in 0 to this, I need to get 0. So when I plug in 0, I'm going to output what? The cosine term, because the sine term is going to go away. So when I plug in 0, the cosine term goes away, okay? Because a of 0 equals 0 forces c1 to be 0 here. And then when I plug in pi, what are we going to get? We need c2 sine of m pi to be equal to 0. But that's easy. I can make m be 1, or 2, or 3, or 4, since m is anything like that. So in other words, I can take m to be 1, 2, 3, 4, any positive integer, okay? Now I can basically get a collection of these things. So for those values of m, what's the corresponding solution to the b equation? The corresponding solution to the b equation is going to be what? Well, in this case, if lambda is equal to negative m squared, then I have that b prime is going to be what? It's going to be positive m squared b. And this is easy to solve. This says that b of t is going to be a constant e to the what? E to the negative m. This is just d plus m squared. So it's going to be constant e to the negative m squared t. Okay, excellent. All right, that's just, of course, solving the simple ODE. So now what we have is the following. So now for any solution, I can write this. I can say that u of xt, any infinite series, the sum, m goes from 1 to infinity, of any constants that I choose here, am, e to the minus m squared t, sine of mx, for any linear combination of these things. This series, of course, is going to converge absolutely and uniformly because it's e to the negative mt squared over here, right? So there's a absolutely uniform convergence of this series over here. As long as the coefficients am are sufficiently well behaved, let's say bounded, for example. Now, what do we need? What do we need over here? So, of course, when we plug in t equals 0 into this formula, we need the result to be f of x. So what do we really need here? We need that f of x is the sum, m from 1 to infinity, of am sine mx. And so, in other words, that's just the Fourier sine representation of f, and so we know those coefficients am have to be over here. So these am have to be the Fourier sine coefficients. So we need over here am need to be Fourier sine coefficients. Okay? And of course, what are those Fourier sine coefficients in the interval 0 to pi? So in other words, this is going to be the solution. So this will solve the PDE. It will satisfy the boundary conditions, and if I choose the am to be 2 over pi, the integral from 0 to pi of f of x sine mx dx, If I make that choice for the AM, namely the Fourier sine coefficients, then this function u of xt will solve the PDE, it will satisfy the boundary condition, and it will satisfy these Dirichlet conditions over here. So this is the heat equation with Dirichlet conditions. Dirichlet conditions over here, because I have 0 conditions on the function itself. So the separation of variables method gives me this infinite series. Now what I can do is I can actually plug this integral over here into the infinite sum, and then write this as a convolution integral, and we'll see how to do that in further videos, and find what the heat kernel is for this interval over here. Thank you very much.